Hello and welcome back to PC Retro Programmer. In the past couple of videos we've been sketching out a skeleton of the Mandelbrot set program that we want to write, and in this video we're going to put some flesh on those bones, as it were. Now you recall we started off with the mathematics of the Mandelbrot set, including the complex numbers, and then we defined this modified iteration that we can use, which will allow us to work with values in the range minus 0.5 to 0.5. And the reason we did that is because these values will be easy to represent and work with on the computer. So I'll start today by just giving a quick summary of exactly how we're going to do that. You might recall that there are two different binary representations on the 8086 and 8088. There's the ordinary unsigned representation, which just uses the binary number system starting from 0 and going up through the positive values. And there's also the 2's complement representation, which allows us to represent positive, 0 and negative values. And the top bit tells us the sign, so if it's a 1, then we have a negative value. So in this particular case, we have a 1 in the top bit, and all the remaining 15 bits are 0 in binary. And this is actually the smallest value we can represent here. It's minus 32,768. And here we have a 0 in the top bit to tell us it's a positive number, and all of the remaining bits are 1, so it's 7FFF in hexadecimal. And that's the decimal value 32,767. So you can see you get a completely different range of values using the binary number system and the 2's complement system. Now it's entirely up to you how you view a value in a register, whether you think of it as being unsigned or signed. There are some assembly language instructions that are designed to work with values as though they're unsigned, and others that are designed to work with values as though they're signed. And also the interpretation of the flags depends on whether you're using unsigned or signed. Now, what's actually going on here in the 2's complement representation is these are actually infinitely long numbers. They extend out infinitely far to the left. And in the negative case, we have all binary 1s in the representation from some point onwards. So if I took a 32-bit truncation of the same number, I would have all binary 1s in the remaining 16 bits here, and they'd notionally continue on forever that way. And if I took a 32-bit truncation of this value, I would end up with all binary 0s. And so this is what the numbers would look like in 32 bits in hexadecimal. The exact same integers, except that we're now truncating at a different point. So that's what's going on mathematically. Now, how do we represent fractional values? Well, it turns out we just need a binary point. So we could use this value for minus 0.5 and this value for 0.5. Well, it's a little bit less than 0.5 actually. In order to represent exactly 0.5, this would have to be 8000. And you can see that there's going to be a problem in 16 bits because this is also 8000 in 16 bits. And we really want to be able to tell whether it's positive or negative values. So you really can't represent 0.5 in 16 bits. In 32 bits, it'd be no problem because you have more bits that allow you to distinguish the sign. So if you want to do a conversion between these integers and these fractional values, you just divide by 65,536, which is exactly what happens when you shift the binary point by 4 places in hexadecimal. So these are the values that we can use to represent our fractional values. Of course, in 16 bits, we suppress the infinitely many binary 1s and infinitely many binary 0s in the number. So long as we've got one bit at least to allow us to tell what sign the value is, then everything's good. And of course, we can't actually put a binary point in a register, so we just have to imagine that those are there. Otherwise, we'd have integer values. So now that we know how to represent our fractional values using 16-bit numbers in our registers, let's actually take a look at the code for the final Mandelbrot set program. By the way, if you can hear some background noise or loud key presses in this video, it's because my primary microphone has died. So we're looking at mandel2.asm, and of course this is just a modified version of the file we had in the previous video. So I'll skip down to this comment here where things start to change. So for most of the calculation, we're going to divide our values through by an additional factor of 2 to make it easier to check for overflows. This is actually critical to how we're going to be doing our implementation. So first of all, it's not expensive to divide by 2 in binary. It's just a shift right by 1 bit. And we have assembly language instructions for this. We have to pick the right one for signed arithmetic. This is called an arithmetic shift, and we have the SAR instruction for that. So it's cheap and easy to do, but why do we have to do that? Well, it boils down to when we're computing 4z squared plus c in the complex numbers, the result could have real or imaginary part that overflows the range minus 0.5 to 0.5. And this is going to be problematic for us for 2 reasons. One, the result won't fit into the allowed range for assigned value in our 16-bit registers. And secondly, if the values are outside the range of minus 0.5 to 0.5, they're certainly outside the circle of radius 0.5, and we should be stopping our Mandelbrot set iterations at this point. Now, it turns out there's a processor feature that's going to help us here. Whenever you do an arithmetic operation with signed values, if the result is outside the allowed range for a 2's complement value in that register, the overflow flag gets set. And so we can actually detect this and use a jump if overflow instruction, JO, to jump off to handle that case. In our case, we're going to want to stop our iterations if we see that. But this overflow feature, which is kind of like a carry for unsigned arithmetic, it's just the equivalent thing for signed arithmetic, this is really relying on the fact that the 2 initial values that we were adding together here weren't themselves overflowed, and unfortunately 4z squared can actually itself overflow. Now we could handle this just by checking whether the value comes back into range again when we add the c. In fact, this might even be possible. It's probably just going to be another overflow, so we could just count overflows here. But that's a bit messy, so what we're going to do instead is just prevent the overflow. And that's why we're going to work with values shifted right by this additional bit, so that the overflow can't occur at this point. We'll add these values together and then we'll shift it back left again by 1 bit, so that we get the value that we should have ended up with for z. And only when we do that shift are we going to look at the overflow flag. The left shift will also set the overflow flag if the result is outside the allowed range. And so that's how we're going to deal with this overflow issue in this code. Now it has a couple of implications for the code that we've already written. Instead of working with A and B starting at minus 0.5, we now have to shift them right by 1 bit, since they're actually used in a part of the iteration where we're using these shifted values. And so that would actually be C000 in hexadecimal. I didn't actually quite use those values. It turns out that the image is just a little bit off center if you use exactly these values, just by a fraction of a pixel, which has implications for the edge of the image, which you can really see. And so to fix this up, just by eye, I added some very small amounts to these starting values, which has the effect of just shifting the image so that it's more centered. You can play around with those yourself to see exactly where we do that. And of course, it avoids the exact value minus 0.5, which is fine to use, but it is right at the extreme of what's allowed for our signed values. So it also potentially avoids some issues there. Now, our main pixel loop is exactly as it was before, still iterates over all the pixels on the screen. What's changed is that I've added now our Mandelbrot set iterations. And we'll do up to 32 iterations for each point. And of course, if it makes it all the way through, then we'll just leave the point black. If it's stopping at some point due to going outside the circle of radius 0.5, then we'll actually use the iteration number to colour the point. So this will actually be the colour value that we use. And of course the iterations are going to count down from 32 down to 0. Now we're going to start with z equals 0 for each of the points C that we're using. And so of course we need to set the real and imaginary parts of z to 0, and those are stored in the SI and BP registers. So now we're all ready to start iterating using this z to 4z squared plus c iteration. So let's take a look at how that actually works. Now I'm actually going to assume that I start this iteration having already computed 4z squared, and that I just need to add the c. Now on the first iteration this turns out to be automatically true because we start with z equals 0, and so 4z squared is still 0. So I really do just need to add the c at this point. And I'll just set things up so that this is always the case every iteration. Now, I don't want any overflows to occur when I do this sum here, and so I want the real and imaginary parts of this sum to be shifted values that I'm adding together. So I'm going to assume that all the values are shifted at this point, and certainly our starting values were shifted, as you saw above. So no overflows here, and now I'm ready to do my shift left by 1 bit to get the unshifted values and detect my overflows. And this is what I talked about above. In that case, we want to stop our iterations and draw a coloured point on the screen. So if either the real part or the imaginary part overflows when I do my shift, then I'll jump to a label called outside circle, which is further below, where I handle all that. Now if I get to here, that means that I was not outside the range, and so I'm all ready to start computing my new z squared value. Now we just use our formula for multiplication of complex numbers for this, and of course we're computing 4z squared, so we'll need 4 times the real part squared and 4 times the imaginary part squared. That'll be part of the computation. Now the real part is in SI, and so remember that the multiply instructions just multiply by whatever's in the AX register. So if I put this value in the AX register and then multiply by AX, I'll actually be squaring. And of course it's a signed multiply, so I use the imul instruction for that. And the result will be 32 bits. It'll be in the DX AX registers. Now to multiply by 4, it's just 2 shifts left by a bit, and so I need to do 2 32-bit shifts, and each of those is just a shift left, rotate through carry left combination. And so now I have 4 times the real part squared. But I need to think about whether any overflows could happen here. Well, I started with values in the range minus 0.5 to 0.5, and I squared them. And remember, squaring a negative value gives you a positive value, so I actually end up with an unsigned result when I do this square, and it'll be in the range 0 to 0.25. And then I multiply by 4, so I'll end up with a value in the range 0 to 1. But this is an unsigned value, and so that'll actually fit in our register, which is really cool. And of course down below I do the same thing for 4 times the imaginary part squared, which the multiplication formula calls for. And the difference of those two values that I just computed there will give me the new real part of 4z squared. To get the imaginary part of 4z squared, I need to compute 8 times the real part times the imaginary part. So I do that in between just so the values don't get messed up in the wrong order. Take the real part, put it in the AX register, and then multiply it by the imaginary part here. And of course I don't want to overwrite the result that I already computed above, so I have to save that somewhere for safekeeping. And we're only interested in the top 16 bits of that. It was a 32-bit result, but we're only working with 16-bit approximations here. So I put that into the SI register for safekeeping. It turns out to be fine to use that because I just pulled the value out of that I need for the last time, and so that register is now free. And so then I just compute 4 times this value. Now, why not 8, since that's what the formula calls for? Well, it turns out from this point on, I want to deal with shifted values. So I want to shift right by 1 bit anyway, and so I may as well just do 2 left shifts instead of 3, and that'll give me the shifted value. And this actually turns out to be the shifted new imaginary component of 4z squared. So I'm done with that, and so I just need to subtract these other 2 values I computed to get the real part of 4z squared. But before we do that, we have to check that we're actually in the circle of radius 0.5. And the reason is that this computation here could have overflowed if that wasn't the case. And actually, it's not obvious why this computation couldn't overflow if we were in the circle of radius 0.5. After all, we could have values here that were in the range minus 0.5 to 0.5, and when we multiply 2 of them together, we could end up with a value in the range minus 0.25 to 0.25. This is not a square here, this is just an ordinary multiplication, so it could be negative or positive. And when I multiply by 4, I'd end up with a value in the range minus 1 to 1. And of course that won't fit in a register. So even if we were in the circle, maybe this could overflow. But it turns out there's a little theorem that we can use here to show that that actually doesn't happen. I use something called the arithmetic mean geometric mean inequality to show that this value won't actually overflow, which is really cool. It means we don't need to do any overflow checking here. But of course, if you didn't know that, you could just do some additional instructions to take care of that. Now, the thing that we need to do is check whether we're inside the circle of radius 0.5, and the way that works is just to add the real part squared and the imaginary part squared and see if we're less than 0.25. But this is easy to do since we already computed 4 times the real part squared and 4 times the imaginary part squared. So if we add those together, all we need to do is check whether this is in the range 0 to 1. And if it's not, it's unsigned values, after all these were squares, then we'd end up with a carry. And so all we really need to do is just add these 2 values that we computed together, and that's this line. If there was a carry, then we're outside the circle, and then we just jump off to our outside circle label. So this is just really cool that we actually had the values computed that we needed here. So now we need to compute the real part of 4z squared, and as I said, it's the difference of these 2 values instead of the sum, and so we're going to need to do a subtraction for that. But in the meantime, we've actually messed up one of these values. We added dx to it, so we just subtract dx back off again, just so that we have these 2 values ready to subtract them. But of course, I'm going to be working with shifted values from this point on, so I actually want to shift these values right by 1 bit. That'll also prevent any overflows here when I do this subtraction. So now I carry out the subtraction, and this gives me the new real part of 4z squared, albeit shifted. So now I've actually computed the real and imaginary parts ready for the next go around, and they're actually in the right registers as well. So I decrement my iteration counter, and if we're not at 0 yet, then I go back to the start of my loop for the next iteration. So that's what this jump if not 0 is about. If this decrement didn't set iter to 0, then it will jump back to the start of the loop. So now I'm going to have some code for dealing with the case where we were outside the circle. This is where we're actually going to draw our pixel. And of course, we have to jump over this code if this loop iteration is finished here. So I just jump down to a label at the end of the program, done iter. So now let's take a look at the code that actually deals with the case where we're outside the circle. The first thing we're going to do is draw our pixel, and nothing could be simpler. We're simply going to move our iter value into the AL register and use our stosb instruction to write a byte into esdi. And remember that di points to the current pixel on the screen, which we've been iterating over. Now, of course, it also increases the DI register, and so we take one back off here just so that we end up without the DI being incremented twice. And so that's literally all that's required for our Mandelbrot set iterations. Now, you might wonder why I decremented DI and incremented DI. Well, of course, if I had jumped over this piece of code here down to here, I really need to still increment DI to move to the next pixel. So that's why it has to be decrement DI and then increment DI. Anyway, this is now back to our original code. We just compare to see if we're at the end of the line, and then if so, then we jump off to deal with that. We update our A value, and of course this has been divided by 2 because we're dealing with shifted values. That's the other change that was made to the original code I rated in the last video. But everything else is the same as what we had in the previous video. So I know that's very long, but that's the end of our Mandelbrot set program. So let's save this and actually assemble it and run it. Let's assemble it and link it as usual. And now let's run it and see the result. And look at that beautiful Mandelbrot set. It's not blazingly fast, but I don't think this is terrible performance for the machine that we're running it on. And as you can see, the colors just work out relatively nicely. There's various shades of grey and a blue outside the circle, and of course black in the Mandelbrot set itself. And then we end up with some little points of various colors. Those are colors where we have a high number of iterations. And so, yeah, this is the Mandelbrot set. Now, what I thought I would finish with today is just a list of things that you could actually try for yourself if you have access to the code. And I will be uploading the code at least in the next day or so. And there'll be a link in the description so that you can play with it and try out various things. So here is a list of ideas that I came up with for you to try yourself. We're doing 32-bit shifts in our code at the moment, and we probably don't need to do that. We're only using the top 16 bits of the result. Now, of course, if you throw away the bottom 16 bits and then just shift the top 16 bits, you will lose 1 bit that way. And this may or may not be a problem, but it's certainly worth a try and could speed things up just a little bit. At the moment, the image is in the left-hand side of the screen, and you could actually put it in the middle of the screen. I think I figured out you can do this by changing just 2 lines of code. Probably if you think about this as just a 1-line change, and then try that out, and you'll realize that this doesn't actually work. And then you can go hunting for the other line that needs to be changed. Another thing you could do is change the colors. For example, you could do some color cycling. This is where you change the VGA palette registers, which is a very fast operation, and you just cycle them around so that the image appears to have a kind of color cycling effect going on, which looks very pretty, but it's very computationally cheap. Another possibility is to zoom to a smaller part of the Mandelbrot set. At the moment we're displaying the whole thing, but if you use different starting values and you use different shifts as you go from pixel to pixel, then you can zoom in on the Mandelbrot set. Now you can't zoom far because we're only doing 16-bit approximations here, but you might be able to zoom a little bit, and this could be a fun exercise. Now, the other thing you could do is try the alternative of counting overflows to deal with the overflow problem that I talked about at the middle of the video. And this may or may not work. I haven't thought this through, but it shouldn't be too hard to implement. And then you might be able to do away with working with shifted values. It's quite a little bit of work, and maybe that's something for someone who's fairly good at arithmetic and basic mathematics. Another thing you could do is just improve the colors that are there. Again, this involves fiddling with the VGA palette registers, or you could even just use different 32 colors. At the moment, I just use the colors 32 down to 0, but you could shift to a different part of the existing palette. There are 256 colors after all. Another possibility is to speed up the drawing by using the fact that it's a reflection about a line across the middle of the screen. So there's no need to compute the Mandelbrot set below the middle of the screen. You just draw the same pixel twice, once at the top and once at the bottom. So this is a good exercise for practicing assembly language programming. And if you want something really challenging, and maybe for some of those very advanced programmers who are watching my videos, despite the fact that this is an elementary one, there is a formula for the main cardioid of the Mandelbrot set, and you could actually skip over that entirely and just not compute any of the points there. These are the most expensive points because they are, of course, maximum iterations. So if you can skip a vast number of those, then you can get this to go a lot faster. I didn't do that when I was a teenager, but I did end up with a slightly faster result than we have here. I think on my 286, I actually ended up with the whole thing being displayed in 3 seconds. And later versions went even faster than that. In fact, I was able to beat Fractint that was available back in the day. So it is possible to speed this up substantially more. Unfortunately, I've forgotten the exact method that I used, and the focus of this video wasn't to do the fastest possible Mandelbrot set. It was really just to use it as an example of how to do loops and how to do jumps in code, especially conditional jumps.